In the video on probability measures, we've seen two different models of a dice throw. One in which we describe the entire trajectory of the die as it flies through the air and rolls, and one in which we only describe the outcome 1, 2, 3, 4, 5, 6. Now, if we're playing a game, of course, the difference between these two doesn't matter as long as the probability for the measurable set representing 1, 2, 3, 4, 5, 6 is the same. So mathematically, we would like to be able to abstract from the set omega to only that part of the outcome that is relevant for us. This is why mathematicians have introduced the notion of a stochastic variable. A stochastic variable is not a variable at all. It's actually a function from the set omega to the real line. And in the case of the dice roll, this function only maps to a portion of the real line, namely only to the set of numbers 1, 2, 3, 4, 5, 6. But as we will see, there are other stochastic variables that measure other things, for example, latencies, times, distances, all kinds of measurements that you can take in which the entire real line is going to be used. Using a stochastic variable, we can abstract from the set omega by simply writing the probability that x equals 3, rather than the probability that the measurable set of all the omega such that x of omega equals 3 is equal to something. So we don't need to worry about how the set x equals to 3 is actually constructed from the set omega. We just assume that this set is measurable. And in the way that usually stochastic variables are chosen, this set will be measurable as long as it is a countable union of intervals. Given a stochastic variable x from omega to r, we are usually interested in the relation between the values on the real line r and the probabilities associated with them. If x maps omega to a finite subset of r, in other words, if x is a discrete stochastic variable, as with the example of the dice, then it makes sense to look at the so-called probability mass function, which is simply defined as the probability of the stochastic variable being at a certain point. On the other hand, if x maps omega to the entire real line, probabilities at single points tend to be 0, and in that case, we instead usually look at the cumulative distribution function, which is defined as the probability of finding a value below or equal to x. If x is discrete, we can still use the cumulative distribution function, but it will get this staircase pattern with jumps at places where the probability is not 0. If x is continuous and differentiable, then it makes sense to actually take the derivative and we get a so-called probability density function. In any case, discrete or continuous, the cumulative distribution function completely characterizes the probabilities associated with a stochastic variable x. So usually when we are building theory, we focus on cumulative distribution functions whenever that is possible. But sometimes calculating with the probability mass function or the probability density function is easier and also feels a little bit more intuitive. From the definition of a probability space, it follows that any cumulative function starts on the left with at 0 in the limit, and on the right it ends in the limit at 1, and it will be always non-decreasing in between. It will always be going up or staying constant. Any function that satisfies this can be used as a cumulative distribution function. Projected onto probability mass functions, This means that the sum of all the instances adds up to 1. And projected onto probability density functions, this means that the area under the probability density function always adds up to 1. What cumulative distribution functions and density functions allow us to do is to calculate with probabilities. For example, if you want to know which is the most likely outcome of a discrete stochastic variable x, then you can simply look at where the probability mass function attains its maximum value. This is called the mode of the variable x. The mode is also defined for a continuous stochastic variable as the place where the probability density function achieves its maximum. Of course, that doesn't mean that that exact outcome has the maximum likelihood, because every individual outcome in a continuous distribution has a likelihood of 0, but around that outcome you will find a measurable set with the maximum likelihood. As another example, often the order of the outcomes is also important. So we've placed the outcomes on the real line, but in principle, if you have a discrete stochastic variable, the order of the numbers may not mean anything. It can just be indicators. For example, if a school teacher randomly wants to decide which children end up in which groups, they may go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 to create 5 groups. That does not mean that group 1 is somehow considered higher or lower than group 5. But of course, if you have a stochastic variable that represents the income in a country, then it may be important which outcomes are graded lower and which outcomes are graded higher. Now, if the order of the outcomes is important, then one of the things that you might look at is the median of a stochastic variable. That's the 50-50 point in which everything to the left has a probability together of 50%, and everything to the right has, of course, then also a probability of 50%. That 50-50 point you can define using the cumulative distribution function as the point where the cumulative distribution function reaches 0.5. By the way, the point where a cumulative distribution function attains a certain probability is called the quantile of that probability. So the 20% quantile of this distribution function is the point where the distribution function achieves 0.2. If you map that to, for example, a continuous distribution function, then you can also look at the probability density function and see that the 20% quantile is the area on the left that in total has an area of 0.2. Now, both the median and the mode do not always exist for every type of distribution. I think you can come up with a few examples in which these two notions do not really make sense. And also, sometimes there may be multiple maxima in a distribution, and there may be a horizontal part of the continuous distribution function at 0.5. So then you also have multiple possible choices for the median. A value that is actually uniquely determined, if it exists, is the mean of a distribution. Studying the mean of a stochastic variable only makes sense if not only the order is important of the values that the stochastic variable may take, but also their relative magnitude. For example, if you're thinking about the income, whether it is important that one income is twice as high or 3 times as high as another income. The mean of a variable, also called the expected value, is usually denoted by E of x. And it may be defined as the weighted average over either the probability mass function or the probability density function. So you can write E of x is the sum over x of x times the probability of x, or E of x as the integral of x over x times the probability of x. F of x in these functions is the probability density function or the probability mass function, whichever one you were using. In its most generic definition, however, you can also define it directly on the cumulative distribution function using a so-called Riemann-Stieltjes integral. So then E of x is the integral of x d fx, where fx capital Fx, with capital Fx being the cumulative distribution function. The intuition behind the expected value is that if you perform a number of experiments, a large number of experiments, and you average out the result, then you will end up with the expected value. I'm going to be more precise about this in one of the upcoming videos on the central limit theorem. One thing that I do want you to realize, however, is that the mean actually is not always defined. If I do a little thought experiment and I take a little laser pointer and I spin it around in the room and I watch where it is going to shine on the wall behind me, then if that wall is very long and the laser pointer ends up at an angle that is uniformly distributed, then the distribution of the point where it shines on the wall is this Gaussian function. Now, the interesting part of this function is that it actually is a distribution. The area under the function adds up to 1. And it has a median that's 0 in this case. The median is that the light shines exactly behind me because the chance that it shines to one side of me is the same as the probability that it shines to the other side. But there is no expected value. Basically because the probability of it shining very far away is very large, and if you try to take the limit to determine the expected value, you'll find out that this integral does not converge. But this is not a course on calculus, so I was actually not planning on going into this example in too much detail. I just wanted you to be aware that such distributions do exist. Okay, so the expected value already tells us a lot about, well, what to expect if we have a stochastic variable. But everybody knows the story of this unlucky hiker who drowned in a river that was only 10 centimeters deep on average. That story shows us that it's not only the expected value that counts, but also the deviations from the expected value that are important. And if we're talking about deviations from the expected value, it may make sense to also try to calculate the expected deviation from the expected value. This is called the variance of a distribution. The variance is a measure for the expected deviation from the expected value. The way it is defined precisely is that we take the square of the difference between the value that comes out of a stochastic variable and its expected value. So E of the square of x minus E of x. This, of course, if you compare it in physical units to the physical unit of a stochastic variable, is squared. So if you want to get back to the original physical unit, you take the square root of the variance, and that's usually called the standard deviation. Just like with the expected value, and even if the expected value exists, the variance of a stochastic distribution does not need to exist. Often we will assume upfront that it does, but there are distributions that defy defining something like this. Proposing a stochastic variable with a distribution stated as a probability density function, a probability mass function, or a cumulative distribution function is the most common way to model any kind of system or experiment. And giving a value like the median, the mean, or the mode helps an audience to understand what kind of distribution you have in mind more quickly, so that helps in your reporting if you reflect on that. And of course, it also helps if you reflect on the variance to avoid this danger of potholes in rivers.